Okay, so we start the recording. Our speaker today is Kun Wang, and his title is the Farrell-Jones and Baum-Connes conjecture in K-theory. So please, Kun, go ahead.
Okay. Thank you very much for the invitation.
We can't hear you. Are you? Can you hear me? Your mic disconnected?
You cannot hear me?
Yes, I can.
He can hear.
Yes, I can.
Okay. So the rest of the world can hear you. Sorry. Go ahead.
So can I start? Yeah. Okay. So everybody can hear me?
Yes, I can. Do you?
Oh, okay. Right. Okay. So yeah, then I will start. So first of all, thank you very much for the invitation to give a talk in this seminar. It's my great pleasure. And today I will talk, a bit about the Farrell-Jones and the Baum-Connes conjecture in K-theory, and then I will try to report my recent work on the construction of a new and concrete model for the equivariant topological K-homology theory, which is defined for all group actions, not just for proper group actions. Okay, so I will first try to talk a bit about the background. I will be focusing on the Farrell-Jones conjecture mainly because personally I'm not an expert in non-commutative geometry. I'm kind of much more familiar with the algebraic K-theory side. Okay, so yeah. So for the background, I will be focusing on the Farrell-Jones conjecture, and let us start with some problems in topology. In topology, finite CW complex they are considered, to be, nice spaces. So a very natural question is, one want to know when a space has the homotopy type of a finite CW complex. Okay, so once you have a finite CW complex, you can further ask, whether it has the homotopy type of a closed smooth manifolds. And finally, when you have two closed smooth manifolds, you want to know whether they are diffeomorphic. Now, it turns out that a satisfactory answer to these questions usually follows a pattern. Okay, so you have a topological problem, and in order to answer it, you need first to put some weaker topological assumptions, and under these weaker topological assumptions, one can develop some algebraic theory, okay, to obtain some algebraic obstructions. And the algebraic obstructions here usually lies in the algebraic K or L groups of the fundamental group of the underlying space or their relatives. Okay, so yeah, that's the usual pattern here. And maybe let us go back to the previous three problems. So the first one is you want to decide when a space is the homotopy equivalent to a finite CW complex. And in order to answer this question, you first need to put some weaker, geometric or topological condition on your space. And here it is finitely dominated. Okay, so here finitely dominated means basically intuitively it means half of being homotopy equivalent. Okay, and under this weaker geometric assumption, then one can obtain an algebraic abstraction, and here called the Walsh finiteness abstraction, which lies in this reduced K group, and your space is a homotopy equivalent to a finite CW complex if and only if this abstraction vanishes. Okay, and for the second problem, you want to decide when a finite CW complex is a homotopy equivalent to a closed smooth manifold. And then, first of all, again, you also first need to put some weaker geometric conditions on your space. Okay, and here they are. The first condition is X must satisfy the Poincare duality, and the second one is X should have a tangent bundle. And under these geometric conditions, then one can construct some algebraic abstraction here. Here is the surgery abstraction, which lie in this L group, and your space is actually homotopy equivalent to a closed smooth manifold if and only if this surgery abstraction vanishes. Okay, but here I have
one little question. Aren't these Ln groups periodic of period 4?
Sorry, I cannot hear you clearly.
The Ln groups.
Yeah.
Right? Aren't they periodic? Of
Yes,
period
yes,
4?
yes.
Yeah, because you write N greater than 1 than 5, maybe.
Sorry, so here I have to, this is a typo. Here, this N is not this N. Okay, this N means the dimension of the manifold. Okay. Yeah. Okay. So yeah.
Okay. Okay.
Thank you. Yeah. Okay. Yeah. So they are different. Okay. And for the third problem, you want to decide when two closed smooth manifolds, they are diffeomorphic in high dimensions. Okay. So in dimensions greater than or equal to 5. Okay. Then first you need to again, okay, to put some weaker geometric condition on your space, and here the condition is that you need to have an H cobordism, okay, between these two manifolds. Then once you have this cobordism between them, we can perform surgery on this cobordism, so to obtain the one-head torsion. Okay, and under this one-head torsion is the abstraction, okay, for your two smooth manifolds to be diffeomorphic. Okay, so here we see that these algebraic abstractions usually lie in some K groups or L groups or their relatives. Therefore, it is quite important to understand algebraic K groups and algebraic L groups of this integral group ring. Okay, so here we can think, okay, G as the fundamental group of the underlying space. And more generally, okay, yeah, we can replace the coefficient ring, okay, Z, okay, by any associative ring, okay, with unit. Okay, and so now next we will be focusing on the discussion of algebraic K-theory. The discussion for L-theory is parallel. Okay, and now maybe let us have a quick review about algebraic K-theory. We can think it as a sequence of factors from the category of rings to the category of abelian groups, and for the lower K groups like K0 and K1, they are easy to describe. K0 is the gross-integral group of the isomorphism classes of finitely generated left project modules, and K1R is the abelianization of the infinite general linear group. Okay, but for higher K groups, they are harder to describe. Okay, so we will not record their definitions here. Okay, so our problem is trying to understand the K-theory of RG. Okay, now the works of Farrell and Jones suggests that the K groups of RG is it kind of depends on the K-theory of its virtually cyclic subgroups and the homology of G. Okay, so that's a rough picture, and in order to make this precise, we need to use the language of equivariant homology theory. Okay, yeah. So maybe next, let us briefly talk about equivariant homology theory. Okay, so here we let G be a discrete group. Okay, so in this talk, every group will be assumed to be discrete. Okay, so a G equivariant homology theory is a homology theory satisfying the equivariant version of the Allenberg-Steinert axioms. Okay, namely, it consists of a sequence of factors from the category of G CW pairs to the category of abelian groups, and there are also boundary maps, so that these factors they are G homotopy invariant. They satisfy the long exact sequence for a pair. They have excision, and they satisfy the disjoint union axiom. Okay, so basically, okay, it's just the equivariant version of the Allenberg-Steinert axioms for the homology series. All right, okay, now for K and RG, and also for L theory, and for the K theory of reduced group C-star algebras, Davis and Luke, Jim Davis and Wolfgang Luke, they have a unified approach for this series, and they made use of a very abstract homotopy theoretic construction to construct the corresponding equivariant homology series. Okay, so here here is for algebraic K homology and algebraic L homology, and also for topological K homology. Okay, yeah. So we have this unified approach. Okay, and we use this notation. Okay, to denote these three homology series, and they have the property that when we evaluate this homology theory at G mod H, so here H is a subgroup of G, then this will give us the K theory of this subgroup. Okay, here RH. Okay. And in particular, if we take H to be G, then on a point, okay, the value of this homology theory is the K group that we are interested in, right? Okay, so we want to understand that, like here K and RG, or it's L theory, or the topological K group of its reduced group C-star algebras. Okay, yeah. So for this, three, like here algebraic K groups, here topological K groups, or algebraic L groups, they have this unified approach. Okay, but a very abstract approach for the construction of the corresponding equivariant homology theory. So, but this abstract construction, it's good for for study some formal properties, but for the actual proof for the Farrell-Jones or the Baum-Connes conjecture for some particular class of groups, this abstract construction is not so convenient. Okay, So for the actual proof, one needs some very concrete construction of this homology series. Okay, now in order to maybe to recall the definition of the statement of the Farrell-Jones and Baum-Connes conjecture, we still have to recall the notion of universal space of group G relative to a family of subgroups. Okay, so here we fix a discrete group G, and here F is a family of subgroups of G, which is closed under conjugation and taking subgroups. Okay, and like F can be taken to be the family of trivial subgroups, can be like the family of finite subgroups, or the family of virtually cyclic subgroups. Okay, then corresponding to this information, there is a universal space, also known as the classifying space of G relative to F, EFG. Okay, this space is characterized up to G homotopy equivalence by the following properties. First of all, this space is a contractible GCW complex. And then secondly, it has the following universal property. For any other GCW complex X with stabilizers lying in the family F, there is a G equivariant map from X to EFG, which is unique up to G homotopy equivalence. Okay, so the following examples, are the mostly used ones. Okay, like when F is the trivial family, then it's the the familiar space EG, right? Okay, and when F is the family of finite subgroups, we usually denote it by E under bar G, and when F is the family of virtually cyclic subgroups, we usually denote it by E under 2 bars G. And when F is the family of all subgroups, then we can simply take this space to be a point. All right, okay, so that's the notion of classifying space of a group G relative to an arbitrary family of subgroups. Now, we can formulate the Farrell-Jones and the Baum-Connes conjecture. For the Farrell-Jones conjecture, we need the corresponding equivariant algebraic K-homology. And for the Baum-Connes conjecture, we needed the corresponding equivariant topological K-homology. Okay. So for the Farrell-Jones, the corresponding classifying space is E under 2 bar G. Okay, so it's the classifying space relative to the family of virtually cyclic subgroups. Yeah, so here we have to take this classifying space instead of E under bar G, because there is the neo group phenomena in algebraic K-theory due to the Abbass-Heller-Swan formula. Okay, so that's the difference. Okay, so for the Farrell-Jones, there is a unique G map from E under 2 bar G to the point, and this map will induce homomorphism on the level of homology groups. And the right-hand side of this homomorphism is simply the group we care about. Okay, so it's K and RG. Okay, so the Farrell-Jones conjecture states that this homomorphism is always an isomorphism, and there's also a theoretical version. And for the Baum-Connes conjecture, it's similar, but the only difference is now the space is the classifying space is E under bar G. Okay, so this map will induce on the level of topological K homology groups. Okay, a homomorphism, and the right hand side is the group we care about, which is the K-theory of the reduced group C-star algebra of G. Okay? And the Baum-Connes conjecture states that this homomorphism is always an isomorphism. Okay, so these two conjectures, can be formulated using this, language. Okay, yeah, using the same language. So they have, a lot, in common. Okay. Now, now a few remarks. The left-hand sides of the assembly maps, they are, because they are homology series, so they are computable. But these conjectures not only provide, a method for the computation of these K groups, they also have, geometric meanings in terms of surgery theory and index theory. So that they imply many other important conjectures in geometry, topology, and algebra, such as the Farrell conjecture on topological rigidity of closed spherical manifolds and the Novikov conjecture on homotopy invariance of higher signatures. Okay, and so now maybe let me make just some comments about the known results so far. So far, the Farrell-Jones conjecture has been proved for a large class of groups, including hyperbolic groups, K0 groups, lattices in almost connected Lie groups, mapping class groups, and virtually solvable groups. But it is still open for some other important groups, such as the amenable groups. And for Baum-Connes conjecture, mainly it's known for groups with Hack-up property and also for Gromov hyperbolic groups and their subgroups. But it's still open, like for lattices in almost connected Lie groups, such as like SL and Z, right? When n is greater than or equal to 3. Now, next I want to discuss a bit about the methods of the proofs of the two conjectures. For the Farrell-Jones conjecture, first we need an appropriate concrete model for the equivariant algebraic K-homology theory. As we have mentioned, the model constructed by Davis and Luke, it's quite abstract. It's not suitable for the actual proof. Okay, so for the actual proof for the Farrell-Jones conjecture, we need a much more concrete construction of the model, and there is one constructed by Arthur Bartels, Wolfgang Luke, and Holger Reich, and some others using the methods of geometric modules and controlled algebra. Okay, so first we need a concrete model, and second, on top of this model, so far the main strategy used to prove the Farrell-Jones conjecture for some class of groups is controlled algebraic K-theory. Okay, yeah, so that's the the main strategy, and in the process of the proof, one also have to make use of relative assembly map and the transitivity principle. So this enables us, to consider the assembly map relative to any family of subgroups, not just relative to virtually cyclic subgroup, that's that's quite important, because that enable us to make use of some more general geometric conditions on groups. Okay, yeah. So some geometrical conditions on groups, naturally, enforce one has to consider not only the family of virtually cyclic subgroups, but also other family of subgroups. Okay, so that's the main method so far used to prove the Farrell-Jones conjecture. Now for the Baum-Connes conjecture, first of all, one also need an appropriate concrete model for the equivariant topological K-homology theory. Okay, so yeah, so far the main one is the Kasparov's equivariant K theory, but this model is only defined for proper group actions. It's not defined for all group actions, and this obstructs the definition of relative assembly maps. And also, so in particular, there's no the so-called transitivity principle. Okay, so that's a difference between the Baum-Connes and the Farrell-Jones. And the main method that used to prove the Baum-Connes so far is the so-called dual Dirac method. And also certainly one, in order to carry out these methods, one also have to put some appropriate geometric conditions on groups. Okay, so so we can see that these two conjectures, they are, in terms of their formulations, they are quite similar, but so far the methods of proof are quite different. Therefore, a very natural question is, one can ask is whether we can carry the methods used to prove the Farrell-Jones conjecture to prove or to study the Baum-Connes conjecture, right? And vice versa. Moreover, the Farrell-Jones conjecture is of algebraic nature, while the Baum-Connes conjecture is both of algebraic and analytic nature, right? So the Baum-Connes conjecture can be kind of viewed as the completed version of the Farrell-Jones conjecture. So in view of this, there is a good chance that the methods for the Farrell-Jones conjecture should, in principle, also work for the Baum-Connes conjecture. Okay, so that's a moral viewpoint. And secondly, there is the Cauchy-Baum-Connes conjecture. The general strategy used to prove the Cauchy-Baum-Connes conjecture is indeed very different from the general strategy used to prove the Baum-Connes conjecture. Indeed, the method used to prove the Cauchy-Baum-Connes conjecture is indeed very it's kind of in the same spirit as the method used to prove the Farrell-Jones conjecture. So yeah, so for the Baum-Connes, the main strategy is to try to use the controlled operator K-theory, while for the Farrell-Jones, yeah, people use controlled algebraic K-theory. Okay, so in view of this, there's a there's a good chance this kind of controlled operator K-theoretical method will also work for for the Baum-Connes conjecture for some class of groups. Okay, but in order to achieve this kind of goal, we first need a new and concrete model for the equivariant topological K-homology. Okay, yeah. Previously, people use Kasparov's K-theory, but this model possibly is not very suitable for the use of operator K-theoretic method. Okay, so we need to have such a new model, and this new model should be suitable for the use of the method of controlled operator K-theory. And secondly, this model should be also defined for all group actions, not just for proper group actions, because then we can define the notion of relative assembly maps, and we can derive and use the very useful transitivity principle. And thirdly, we can also make use of some more general geometric conditions on groups, such as the geometric conditions formulated on groups from which the Farrell-Jones conjecture can be deduced. Okay, so yeah, we need such a model, okay, yeah, for the equivariant topological K-homology. And my recent work here is, I have constructed such a concrete model. Okay, so maybe next, let me trying to, very briefly outline the construction. And for more details, you can look at my paper. Yeah, it's on arXiv. Okay, so here we let H be a separable, be a fixed separable infinite dimensional complex Hilbert space, and XY be sets, and then we can form this space. I denote it by X double X. It's just the direct sum, of this Hilbert space indexed by the set X, and it can be defined, in this way. Okay, it's the set of all maps from X to H, so that the sum of this square is finite. Okay, so that's the space Hx, and it's a Hilbert space naturally.
Sorry, is that like L2 of X times the natural numbers? Is that, I mean, if I fix H to be L2, little L2,
yeah,
the square summable sequences, then isn't Hx little L2 of the Cartesian product of X and the natural numbers?
Oh, yeah. Yes. Okay. So intuitively, one can think like at each point of in X, there is a Hilbert space H. Okay. Yeah. For every point X in the space X, there is a Hilbert space. Okay. So there is kind of a loss of Hilbert space over X. Yeah, we can think it in this way.
Like a bundle.
Yeah, a bundle. Yes. Okay, and now for a bounded linear operator, so now we have two sets, okay, Hx and Hy, and we consider a bounded linear operator from Hx to Hy, and for any points X in X and Y in Y, we can consider its Yx component. It is defined to be this composition. Okay, so here iota X is the inclusion of the x summand in hx, okay, to hx, and pi y is the orthogonal projection of hy onto its y's summand. Okay, so here, on the left you have hx, on the right you have hy, and here you have a point x, and there is a Hilbert space, right? And here you have y, here you have a Hilbert space. So basically, it's tyx is just from this Hilbert space to this is Hilbert space over y. Okay, yeah, and in this way, we can think T as a matrix, right? Okay, of operators on H, indexed by y times x, right? Okay. And now in this way, we can define the notion of support of T. So the support of T is the set of all points yx, so that Tyx, this component, is non-zero. And yeah, we can also define the notion of locally compactness. That means, so we call T is locally compact if every of its component is a compact operator. Okay. Okay. Now we assume there is for these two sets there is a group action. Okay. So suppose Gx on x and y from left, then we call this operator is G invariant if its component satisfy this invariance property. So the component at the Gygx is the same as the component at the Yx. All right. Okay. Now we are going to construct this Cg times x, this algebra. So this algebra, it is defined to be the set of all bounded linear operators T from H G times x to H G times x. And we require T satisfy the following properties. First of all, T is G invariant. Okay, so here G, x on G times x, diagonally. Second, we require T is locally compact. That means every of its component is a compact operator, right? And thirdly, we require T is G finite. That means we can find a finite subset F of x, so that if this component is non-zero, then G inverse x and G prime inverse x prime should lie in F. Okay, so that's the notion of G finite. Yeah. So basically, this means this operator T is supported, on a G cofinite subset of G times x. Okay, and lastly, we require T has the finite propagation in the G direction. That means we can find a finite subset S of G, so that if this component is non-zero, then we require G inverse G prime belongs to S. So this condition is kind of, come from that, when you consider the group algebra CG, right? So group algebra CG, it is a finite sum, right? And so this condition corresponding to, this finite sum, okay? Yeah. And it can be shown that this set is a star subalgebra of the C-star algebra of all bounded linear operators on Hg times x. And then now we define this C-star G times x to be the norm closure, okay, of this star algebra inside this C star algebra. All right, and one can show that here the C star algebra constructed in this way is always stably equivalent to the reduced group C star algebra of G.
Sorry, is this independent of the cardinality of X? Can X be, uncountable? Or?
No, it's independent of X because we have this, in the definition of this CGX, G times X, we require T is G finite. Okay, yeah. So yeah, that's a very crucial a control condition. Okay, yeah. Yeah, then one can show that this is always stably equivalent to this reduced group set algebra. In particular, they always have the same K-theory, right? The K-theory is independent of X. But our goal is trying to, construct some algebra whose K-theory, really depends on the topology of X. Okay, so in order to do this, one has to to use the technique of localization algebra. Okay, first defined by Guoliang Yu. Yeah, so Guoliang Yu, he used this localization algebra technique to prove the Baum-Connes conjecture, for some very large class of groups. Okay, yeah. So next we are going to make use of his localization algebra technique, but we have to here in Guoliang Yu's definition, he requires the underlying space is is a metric space. Yeah, there's a metric, and then he uses its metric, okay, yeah, to define the localization algebra. But we want to define the localization algebra for not only for metric spaces, but for more general topological spaces. Okay, yeah, may not have a metric, so we have to replace the metric control condition, okay, by the so-called equivariantly continuously controlled condition. Okay, and this condition is actually used in the construction of of a concrete model for the algebraic K-homology theory. Okay, so maybe let me briefly talk about what is equivariantly continuously controlled condition. So here X is the topological space and G is a discrete group. A subset E, which is contained in X times 0 to infinity. Okay, yeah. So this subset is called equivariantly continuously controlled at infinity if the following conditions hold. So it's a bit technical. Okay, yeah. So maybe later. So first condition is for every point X in the space X and every GX invariant open neighborhood of X, we can always find a positive number n and a smaller GX invariant open neighborhood, okay, V, which is contained in U. Okay, so that if T is bigger than n and x1, x2, T is in E, then one of x1, x2 lies in V, implies the other lies in U. Okay, so intuitively, this means when T is very large, x1, x2 should be very close. So when X has a metric, and then one can think of this as when t goes to infinity, the distance between x1 and x2 goes to 0. Yeah. So yeah, that's use original definition. Okay. Yeah. And so the first one is the key requirement, and for the rest three requirement, they are just for some technical convenience. And so second, we require E is symmetric. Okay, that means when x1 x2 t is in E, then x2 x1 t is also in E. Thirdly, E is T invariant, and lastly, we require the diagonal belongs to E. Okay. Okay, so that's the notion of equivariantly continuously controlled condition at infinity. Okay, and we use this notation to denote the set of all such sets. Okay, now using this notion, we can now define the notion of localization algebra in our setting here. Okay, yeah, so here we denote it by CL G times X. So it is the set of all bounded and uniformly continuous functions from this interval to this algebra. Okay, we constructed previously, and we require it to satisfy the for.
So sorry, the algebra. Your notation for the algebra is the uncompleted one, right? C of G times X is before norm completion or after.
Right. Before completion, yes, yeah. Because to really state, the control condition, we need before completion. Yes. Okay. Yeah. So yeah, we require this F to satisfy, here F can be thought as a family of matrices parameterized by T. Okay, by T in this interval. Okay, so you have a family of matrices. Okay, and this family of matrices have to satisfy the following control conditions. First of all, there is a finite subset S in G, a compact subset K of X, a G invariant countable subset lambda in X. Okay, so the cardinality of X may be very large, okay, maybe huge, but we impose this control condition, okay, on its support, right? G invariant countable subset, okay, lambda in X, and an E which is equivariantly continuously controlled, okay. So that for any T, if Ft, the component of Ft here is non-zero, then we require is G inverse G prime in S, and X prime in lambda, G inverse X and G prime inverse X prime is in K, and X prime Xt is in E. Okay, so intuitively this means when T is very large, the matrix, say mainly concentrate on the diagonal, near the diagonal. Okay. Yeah. Okay. So that's the algebra. Okay. Yeah, it can be shown that it's a star algebra in the C-star algebra of all bounded and uniformly continuous functions from 0 to infinity to this C-star G times X. Okay, so it's a star algebra, and its norm closure in this in this algebra, okay, will be denoted by phi star L G times X. Okay, yeah. So that's the construction of the localization algebra here, and you can feel that this localization algebra will really depend on the topology of X. Okay, yeah, because so it's when T becomes larger and larger, the support, okay, tend to near the diagonal. Okay, and yeah. Okay, now yeah, we can define what I call the LK group. Okay, yeah, I define this LK group to be the K groups of this localization algebra. Okay. One can also define, for a pair, if there is a subspace A inside X, then we can also define a relative version. Okay, yeah, but that is a bit technical, so I'm not going to talk about it here. Okay, yeah. So now my main theorem is the following. Yeah. It says that these LK groups they form a G equivariant homology theory on the category of G CW pairs. And when we evaluate this LK on G mod H, okay, on this coset space, then it will give us, the K-theory of the reduced group C-star algebra of H. And in particular, when H equals G, okay, then in this case, G mod G is a point. So when H equals G, it gives us, the K-theory of the reduced group C-star algebra of G. Okay, and that's the group that we are interested in, right? Okay, so that's our main theorem, and this homology theory, is defined for all group actions, not only for proper actions. That's quite important. Okay, in order to carry the general strategy used to prove the Farrell-Jones to study the Baum-Connes. Okay. Now, yeah, so because this LK theory is defined for all actions, we can define the notion of relative assembly maps. That's, yeah, relative assembly maps, as I have explained. Okay, it's quite important, yeah, in the process of proving the Farrell-Jones conjecture. So suppose we have two families of subgroups of G, okay, F, which is contained in F prime, okay, then there is a unique G map from this classifying space to this classifying space, from EFG to EF prime G. Okay, this map is unique up to G homotopy. And this map will induce on the level of homology theory, okay, a group homomorphism, and this is called the relative assembly map from F to F prime. And in particular, when we take F prime to be the family of all subgroups, then EF prime G is simply a point, right? And LK, its value at a point is the K-theory of our reduced group C-star algebra. Okay, so in the special case, yeah, in this special case, when F prime is the family of all subgroups, then this relative assembly map, reduced to this assembly map. So from ALK EFG to the K groups of our reduced group C-star algebra. Okay, and yeah. now the using our ALK theory, okay, we can formulate the Baum-Connes conjecture in the following way, and indeed we can form the Baum-Connes conjecture for any family of subgroups. Okay, so suppose F is any family of subgroups of G, and then we have just constructed this assembly map. So the Baum-Connes conjecture for G relative to F is the statement that the assembly map here is an isomorphism. And when F is the family of finite subgroups, then this is just our usual Baum-Connes conjecture. Yeah. Okay. Yeah. Now, so here that's the Baum-Connes conjecture, and we have the notion of relative assembly maps. As we have mentioned, it's very important. And the last thing is we also have the so-called transitivity principle. So this principle is very useful for determining whether a relative assembly map is an isomorphism or not. Okay, so it says the following: suppose you have two families, F and F prime, with F contained in F prime, and you want to decide this relative assembly map is an isomorphism or not. Then this principle says you only have to check the following. You consider an arbitrary subgroup in your larger family F prime, and you're trying to decide for this subgroup, for this group H, if you can show that the Baum-Connes conjecture for H relative to H intersects the smaller family holds, okay, then this original relative assembly map is an isomorphism. Okay.
Sorry. So when you write H inter F, you mean relative
H
to
intersects
the
every
F which are in H.
Yeah. So H intersects every element in F.
Mm-hmm.
So F will it consists of some subgroups, right? So I let H to intersect every element, every member in F. Yes.
Yeah.
And
so as F is closed under subgroup, this is the same as saying that the elements of F which are subgroups of H.
Yes. Yeah. Yes. Okay. Yeah. And this condition is usually easier to check because H is usually is not a very large group. Okay, so this condition can be checked, not so hard. And then if this can be checked, then this relative assembly map will be an isomorphism. Okay, so now if in addition, therefore, if in addition the Baum-Connes conjecture for G relative to the larger family F prime holds, okay? Yeah, suppose the Baum-Connes conjecture holds for G relative to the larger family, and if we can verify, if we can show this relative assembly map is an isomorphism, then we can deduce the Baum-Connes conjecture also holds for the smaller family. Okay, yeah. So that's a very useful principle, yeah, in the proof of the Farrell-Jones conjecture. Okay, yeah. So my my model here, has all the wanted properties, and so I, in my opinion, there is a good chance, yeah, this new model may be used to study the Baum-Connes conjecture for some class of groups. Okay, so I think that we'll stop here. Thank you. Yeah.
Thank you very much. Very nice, interesting talk. Are there questions from the participants? I see some applause there, but so far. Okay, so if there aren't questions from the audience, I mean, a meta question. So, I mean, in the Farrell-Jones case, something similar is done, but where instead of algebras, you have categories, right? So you have categories of control modules over the space, blah, blah, blah. But usually there is a shift in the K-theory index, right? When you go from the left-hand side, you have some Kn of some category, and you go to Kn-1 of the group algebra, which is not present here. I think in use formulation is also such a degree shift occurs.
Yeah. So here there is no degree shifter. Yeah.
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 That's a good thing. And also, what I was going to say is, I mean, it would be pleasing to me to have a formulation of this Farrell-Jones assembly map, where the left-hand side is also a K-theory, not just of some category, but of some ring. And do you see any chance that these methods of yours you can drop the topology or replace it by some? So, for example, you take some matrices indexed by some Hilbert space, by some space or some set X, which take, at each point they are compact operators, right? So, well, now you want to do this algebraically, so at each point there are finite matrices, or well, coefficients in your ring of interest. And when you have a continuous function from 0 infinity to somewhere, then you take a simplicial model of this and look at piecewise polynomial functions, etc. So, do you think that doing such a translation would make sense and would make it possible to formulate Farrell-Jones in similar terms?
You mean use this kind of localization algebra technique to formulate the Farrell-Jones?
Yeah. So instead of yeah.
Yeah, but so here because the Baum-Connes side here, we can use some, like we have, we needed the notion of, continuity, right? So it's a
yeah, but if you take simplicial models of everything, you just need simplicial maps.
Simplicial maps, okay, yeah. That might be possible, yeah. That one can try, yeah. So basically, you also want, a family of matrices parameterized by by t, right? Okay.
Yeah, yeah. Well, so I mean, the t does occur in as you write it, as parameterized by a continuous parameter, also appears in the Luke Bartels Reich formulation of or Farrell-Jones of the left-hand side using these categories of controlled modules.
Yeah.
Well, but if absolutely necessary, and if you do have to use some simplification model, you can use it. You just think of zero infinity as a sequence of segments, right? And functions which are polynomial in each piece. But
that's I have not thought about it, but that's maybe may work. Yeah, I'm not so sure right now, but yeah. Okay.
I mean that's an old idea that I've had. But it's it's not so easy to implement.
Yeah, right. Certainly a direction of one may think about it. Yeah.
And have you been going back to Baum-Connes precisely? Have you been thinking of some particular class of groups where you think it might be easier to apply your
Yes. So I'm right now trying to working on this. Trying to really see whether my new model may be used to prove some of the groups using the strategy of Farrell-Jones. So I think there is a general strategy,
the pinching
framework. Yeah, general framework. If that works, then for example, like SLNZ, okay, yeah, the Baum-Connes for SLNZ, when n is bigger than or equal to 3, okay, can be proved. Yeah. Yeah. So, but I think certainly it will. I mean, if that general strategy works, then certainly it will. One can certainly prove a quite large class of groups of for the Baum-Connes. So right now the main, I mean, the key is trying to see whether the general strategy, okay, the general framework still works.
Yeah. So whether, I mean, the obvious thing would be to take some of the classes of groups for which the Farrell-Jones conjecture has been proved, and see if the methods can be adapted. Yeah, but I thought perhaps you had a particular class in mind. Right.
Bartels, Luke, and they have formulated a very general geometric conditions on groups where the Farrell-Jones conjecture can be deduced, and and they have this general strategy for the proof. So if the general strategy still works for Baum-Connes, then these very general geometric conditions can also also works for Baum-Connes, and and a large family of groups satisfy their general geometric condition. Yeah. Yes. Okay. So now I mean I'm not particularly thinking about some kind of groups. Okay. I mean right now.
But whether the general strategy applies.
Yeah.
That's your question. Yeah.
Yeah.
I see. Okay. So if there are no further questions, I will stop the recording.
Okay.